Repeating, good afternoon everyone, including those online. I'm Professor Anderson, and I'm very proud to receive here today my friend Simone Milani. He's a professor at the University of Padova, the north of Italy. He will talk about reconstruction of 3D models from different sources, and he will also talk about a little bit of the University of Padova. And he's here to visit us to establish new collaborations, especially in the areas of computer vision, digital forensics, and machine learning. So it's very, very good to have you here, Simone, today. Simone here, I met him back in 2013, and since then we became very good friends. He was then doing his postdoc at the University Politecnico di Milano, in Milan, Italy. And his main interest is in digital forensics, and nowadays machine learning, computer vision, and all of the connecting pieces of these different areas. He's also a very strong guy in digital signal processing. So thank you very much for being here today, and the stage is yours. Please feel free to talk about your research. Talk to us about your research. Thank you.
Thank you very much. Muito obrigado. And so, actually, the talk today concerns the reconstruction of 3D models using heterogeneous sources. By heterogeneous sources, we mean images, okay, that you can collect from the web. I'm going to start the talk just to present a bit where we come from, where this work comes from, so the University of Padova. And it's going to last about 5 minutes, and then we're going to dig deeper into the topic. So, actually, University of Padova, I have some slides regarding where we are. Is one of the oldest university that you have in Italy. Actually, we are located in the northeastern part of the country, so basically, if this is Italy, here we have our region, the Veneto. This is Venice, and here we have Padova. So we are very close. The Venice and the history of the university is really close to the history of the city of Venice. Actually, the city is a bit quite smaller with respect to Campinas. We have only 210,000 inhabitants. And some of the places that are mentioned here are some historical places that you can visit. One of the most famous one is the Basilica of St. Anthony, which takes the name from the city, okay, where the relics of St. Anthony are kept. Of course, we have this quarrel with Lisboa, because they say that St. Anthony was born in Lisboa, so it should be named St. Anthony of Lisboa, but basically, so we share the center with the Lisbon. So, actually, the university is one of the oldest that we have in Italy, and one of the biggest. We have 60,000 students, which is a quite impressive number with respect to the 200 inhabitants of the city. And we have more than 2,000 professors, 12,000 graduates every year, and we have 32 departments ranging from literature, medicine, engineering, computer science, biology, and so on. Actually, the university was founded in 1222, so in 3 years, we are going to celebrate our 800th birthday. And the university was founded by students and professors. But precisely, there were people coming from the University of Bologna. And the University of Bologna, at that time, it was controlled by the church. So these guys were not free to study and investigate the subjects that they wanted to, especially as far for what regards medicines and science, typically because the church prevented them from covering certain topics. And this is why they moved to Padova, and there they found the protection of the Republic of Venice, and there they founded their own university. It is the 5th, 6th, depending on what is the criteria of ranking of the which was founded, so of the world. It is the first founded by students. And actually the tradition, okay, students are important in University of Padova, such that for many centuries the rector of the university was chosen among the students. The motto of the university is the Universitas Patavina Libertas, which means the libertas, the freedom at the University of Padova, Patalina, is universal, which means it's total, so on all the subjects, and universities for everyone. And in fact, this was one of the few, only university for many centuries that did not force the students to take a vow of faithfulness to the Catholic religion. And that is why we had students for many centuries belonging to the Protestant world. We have Jewish students as well. So there were no constraints about who could attend and what they could study. And these are some of our previous alumni. More precisely, actually, Nicolaus Copernicus was one student of Padova. Instead, Galileo Galilei was one teacher of Padova. He taught in Padova for 18 years. And also another alumni that we have is Lucrezia Conaro-Piscopia, which is the first woman who got graduated. And she had a very interesting story, on how she got graduated. And after her, we had to wait several years and centuries before we had another woman graduated at the university. Actually, we have a very old botanical garden, dates back to 500 years ago nearly, and has been renewed with new wings. We also have some really historical places, but that's also very modern one. This is a picture which has been taken outside our department, where during the summer, during the autumn, there are a lot of banquinhas, or where you can buy food and have a drink with your friends. Research is extremely important, so beside this, University of Padova, and both in the medical engineering field. More precisely, it has been ranked for many years. This data dates back to 2018 as one of the first universities, if not the first, for research in Italy, according to the Ministry of Education. We also had an evaluation on November this year, the past year, which basically, as a result, ranked the University of Padova as the first among the big universities in Italy for the quality of the teaching subject. But of course, also if we look this is not only our ministry that say this, it's also, if you look at other ranking, it says that the quality of research is really good. We have a strong dedication to promote the international mobility of students. That's why we have a lot of exchange programs, especially with other European countries, but not only. We have exchange programs with Taiwan, China, North Africa, and other countries which are not included within the European Union. And also we have strong dedication to this international mobility, since we promoted a lot of courses which are entirely in English, included also our course, which is the course of ICT for Internet and Multimedia, which is a course dedicated to ICT, fully taught in English, with double degrees, exchange programs with other universities. And so a lot of people are coming because they can find courses which can be accessed without any problem. This is our department, where we work and study. More information here on the website. Going into details, this is my research group. We are 3 faculties. We have at the moment 3 PhD students, but there are other 3 coming. We have something like 10, 20 master students, and similar amount of students for what regards the bachelor degree. And our courses that we deal with are digital signal processing. This is our core, the topic where we were born. Then we have computer vision, 3D augmented reality, source coding, digital forensic, and immersive communication, which is taught for social scientists. It is a highly interdisciplinary research group, so we deal with machine learning, robotics, network security, so many topics that converge into this group. And research issues that we follow goes from multimedia forensic to classification, 3D processing, up to navigation and a control system, until the coding and transmission of 3D video. We are working recently on augmented reality visor, and then we have some collaborations also with our external societies, working using, for example, visor like HoloLens or Magic Leap 1. We also have a research work that is going on new coding standards and on the semantic segmentation classification of images and 3D objects. Of course, forensic analysis of data from social network is another topic that we are dealing with in this period. So these are part of our industrial collaborations, okay, that span all over Europe and also includes as well United States. And also we have some collaboration with other universities, okay, in Europe, in Australia, and in the United States, and also we hope to add, okay, Unicam, we're adding Unicam to this. Okay, so sorry for taking long on this, so we will go deep and straight to the topic of today, which is the reconstruction of 3D models using this heterogeneous source. So at first we are going to have a review of how it is possible to generate a 3D model, okay, very quick one, and then we are going to focus on which is the main strategy to reconstruct a 3D model from multiple images, which is multiple heterogeneous images, so taken in different location by different people without any order or constraint. And this main algorithm is the structure for motion algorithm, and we will review the different parts of the structure for motion algorithm and see how different people have dealt with the problem and what solutions have been proposed in order to improve the quality and the robustness of the reconstruction. And then we will see what we have added, okay, to this problem by presenting in the end some of the solutions we proposed. So actually, recently we have assisted during the last years as a 3D revolution, since 3D models are used in a wide number of different applications spanning from entertainment to the human-computer interaction, video surveillance, medical imaging, augmented reality, robotics, problem in industrial production, the printing, okay, and of course in forensics analysis. Why are you using 3D? 3D provides more information about the object, so you have a better characterization of reality, and this better information that you provide to the object enable your application or enable people or programs to do things that before it was not possible to do. We know, for example, that human-computer interaction received or made a giant leap forward when, for example, 3D sensors like Microsoft Kinect were introduced and commercialized. Because using 3D information, it was possible to give commands, to make the machine understand commands in a much easier way with respect to the previous tradition that were processing a static or a standard RGB image. So 3D reconstruction methods are important, and we can divide them into two main categories, especially those methods that are based on light, so on cameras. So we have a first method, first category, which is the passive methods. And passive methods means that I simply take an image, I take a scene, and from the scene I collect different images of the scene. So in this passive methods, a first method is the single image 3D reconstruction. So what you do, you take a single image, and then using a machine that has been trained to reconstruct 3D structures, you process this image and you generate a 3D version of the image. The first approach, one of the first approaches that we used and was really diffused one is Make 3D, okay, by Cesena and other people. And this process divides the image into small segments by using, which are called superpixels. So it's not a pixel, something more, but it's not a full segment due to segmentation. Assume that the segment is planar, and then reconstruct by using an SVM, an SVM machine learning strategy, the 3D orientation and depth of the image. And then we have another strategy which is more recent. Basically, it is based on a neural network, and given one view input to this layer, it has been trained on a set of possible object, and given this view, it is able to generate a 3D version, a 3D reconstruction of the object in itself. Of course, in this case, you need a large dataset to train. You have some problems related to overfitting. Instead, the problem of overfitting was also present in the approach by Saxena, and anyway, this proves to be much more robust with respect to this initial solution. The problem is that if you want to reconstruct 3D, you need more than one view. So that's the real point. So 3D methods that process a single image are nice, can be used just to provide a nice visualization to people, but they are not precise. So if you want precision, you need something more. And starting from the human vision, we perceive three-dimensionality because we perceive different views. We have two eyes, and we have very fast saccadic eye movement that allows us to acquire different viewpoints of the scene. Basically, starting from this, you need multiple views of the same scene to have an accurate reconstruction of the reality. So, in order to do this, a first solution that has been proposed for the reconstruction were stereo systems. Stereo systems were used since the beginning, so you can see this dates back to very many years ago, and there was a stereo camera. And stereo system, basically, what you do, you take a camera, you couple with another camera, and these are sort of mimicking of your eyes. Given these two views, it's possible to reconstruct the 3D structure of the reality. This is an example here where you see that this camera here see that the two bones are superimposed. This camera perceives that the two bones are not superimposed, are detached. And this allows you to infer which is the 3D structure of the scene, which implies that this is detached from this, is a different object, and this is placed at a certain position, this is placed in front of the green ball is also in front of the orange ball. So this can be expressed in a much more precise way. So what stereo systems do? They take two cameras, okay, they have two images, they align two images such that the pixel of one point of this associated with these pixels is projected on a pixel which has the same coordinate on the other image, and then they look for the corresponding point in the other image. How do you look this? They search, okay, along a line, and by searching along the line, they compute matching measurements, which are, for example, can be in this case is the difference, is the distance, and you have in this position 37, then you have 16, then you have 12, and choose the points which minimize, for example, these metrics or maximize this metric in case we have a similarity metric. So by doing this, stereo system allows us to say that the point at position UV corresponds to the point U plus D, okay, placed in the second image. But in using this difference, this correspondence, okay, it is possible to compute that map, a disparity map, okay, of the scene, such that for objects which are closer to the camera, the disparity is going to be larger, okay. For objects which are farther from the camera, the disparity is going to be smaller. So this is the basic system that is of multi-view reconstruction and also structure for motion. The fact that we have two images, okay, you can compute the 3D structure of the world. What we must remember in this situation is that these two cameras are perfectly calibrated. So I have done a procedure on these two cameras that allowed me to understand which is the exact orientation of the second camera with respect to the first one, and also understand which is the estimate, which is the position of the second camera with respect to the first one. So this information is fundamental in order to do this process. So these images were obtained because I have the calibration of the images. And it is fundamental if you want to have a dense reconstruction of the 3D world. If you don't have this, you may have some problems we will see in structure for motion. So the advantages of this system, it is passive, it is not expensive, easy to accommodate motion, and able to adapt to different scenarios, so you don't need to track different systems. The disadvantages is that, okay, that you needed to have features. I mean, you needed to have some texture, some information which is possible to track in the two images. If you have a subject like a statue or something, a wall, which is perfectly uniform, it is not possible to estimate the 3D structure of the scene. It has a poor reconstruction when you are close to the object silhouettes, and you can have problems when you have no match surfaces. Adding other cameras, so creating a multi-view system, it helps the reconstruction. And this is the case, for example, for multi-view and classic structure from motion strategies. You have many cameras, more than two, okay, and you can process all the images taken by this camera in couples, like if they were stereo systems. And in a multi-view, all the cameras are calibrated. In a classical structure from motion, what you do, you have a video, okay, and you assume that this video taken by this camera, the scene is static and the camera is moving around the scene. So what you can do, you can associate every frame, which has been taken in a different instant, to a different camera. So this is instant k-1, this is instant k. I can assume that I have two different cameras taking a stereo view, okay, of the scene. And this is quite used, and the classical structure from motion exploited the fact that having a video, the difference between one frame and the following one is really little. Okay, you have and you also have an order between frames, so you know that frames sometimes can be coupled, can be associated to frame at time t+1. This is crucial. We will see for the reconstruction, but the advantage is that feature tracking can be easier because I can use optical flow, I can use other types of strategy in this case. Temporal continuity, okay, you can be exploited. You can use also differential geometry. But the problem, of course, if you don't have texture, you are still in trouble. And of course, if you have object moving, you still are in trouble. Unless for multi-view camera, where especially multi-view camera are used also to track object in motion. So the difficult part about multi-view system is that when you don't have this information, where the images are collected in the wild. So you go on Flickr, you just digit as an hashtag or one place, let's say San Marco Square in Venice, and you start collecting images from Venice, okay, which can be taken by different people at a different time, in different days, with different subject and different conclusions. So for example, you download the image of one Japanese tourist that is taking a picture of the Basilica, with his wife in front, and then I have another guy with a group of friends, and so on. So, despite this, structure from motion is able to order these images involving the reconstruction and throw away the elements in the image which are not significant for the reconstruction, and then create a 3D model. At the same time, together with creating a 3D model of the scene, it is possible to localize and orient each image or the camera that is taking the image. This is a video, for example, of taken from Bandler, where you can see this is the reconstruction of San Marco Square in Venice. All the triangles that you see, all the cones that you see, the pyramids that you see, are a representation of the cameras, of the images that have been taken, an image that have been used in order to have the reconstruction of the scene. The idea of this type of strategy are used, for example, for cultural heritage applications. Of course, if you want to do some analytics on big data, just imagine in a city, you collect images from different cameras which are spread all around the cities. Can be used in geoscience, forensic reconstruction, and many other applications. We also have some active methods, which I will go through really quickly. Basically, active methods are those methods where you project something on the scene. This is necessary when, for example, you have a scene where there are no texture, for example, a wall. In that case, the solution provided by active methods, let's say in a very quick way, you can say that this solution basically projected the texture on the surface of the object. And we go for the first method, which is Kinect version 1. The scientific name of Kinect version 1 is structural light camera, infrared structural light depth camera. What happens, basically, there is an infrared projector that projects a set of dot pattern on the objects, and there is a camera that collects this pattern of dots, and according to the distortion, it is possible to estimate the 3D strategy of the 3D structure of the scene. It is like if I put myself in front of the projector. So in this case, the projector is projecting on the wall, which is perfectly flat, and you can see the image, the slides, perfectly equal to what I see, for example, on my laptop. If I start and I put in front between the wall and the projector, basically the image is distorted, and this distortion allows to estimate which is the shape, okay, of the scene. We have another strategy, which is time of flight. In this case, it is Kinect version 2, but the scientific name is time of flight depth camera. In this case, we are exploiting basically the traveling time, okay, or time of flight, from the emitter, which emits the infrared light, to the sensor. So if I have this device here, emits an infrared light, which is modulated. It is acquired back after it has been reflected by the 3D surface, and I can compute the phase difference, okay, and this phase difference allows me to estimate the distance of the surface with respect to the device. I can do this for a matrix of points, and doing this for a matrix of points, this allows me to obtain the depth image as well. So these are very nice methods. The problem is that they work really well. They work if you don't have texture and smooth objects. Of course, they work at a high frequency, so they allows you to acquire dynamic scenes. The problem is that they are using infrared radiation, and therefore they can be affected by other external infrared radiation, like, for example, the sun. So most of them are used in indoor, okay, environments. If you use outdoor, you have to increase the emission power of the device, or you have to use something else, okay, like stereo system. So that's the point. 3D laser is another strategy which uses the same principle, but the consumption is really high and it's really slow. So for many applications, these are really useful tool, but for many others you have to use stereo applications, stereo systems. So when we use, okay, structure from motion, so just to recall what we already said, we collect these images from the web. So the idea, the initial idea about structure from motion from web harvested images is the classical structure from motion. So there is a camera moving different images taken at different instants, and these images can be basically coupled, and I can couple different points of each image corresponding to the same 3D point, okay, in reality. And I can use this coupling information to reconstruct, okay, the 3D structure of the world. There are different softwares that you can use to do this. I just mentioned some of them. So Bundler is the first one. It was first published in 2006 by Snavely. Then you have Visual Structure for Motion, where there is a nice interface, okay, graphical interface, and dates back to 2010. Then Samantha is another software which was developed by Andrea Fusiello at the University of Udine. And then we have ColdMap, which dates back to 2016, is one of the most recent ones. And basically, these are those that are really, let's say, robust, okay? They've been used a lot of times. People are using as a comparison terms for their algorithms. And also this has been commercialized. There is a society that is commercializing Samantha. And other ones are free for download. And what are the main problems related to 3D reconstruction from crowdsourced data? So images divided provide a lot of information, too much. So we need to select, okay, which is the information that we need, okay, to use. And we also needed to understand how to process them. So what are the features that we need to extract, which is the order, how we need to combine them together, and so on. And from this structure for motion strategy, okay, we need, for these reasons, we needed to understand whether the image is useful, okay, or we can discard it, which is the order of the image, and which is an effective triangulation solution that we needed to obtain. Finally, for these models, if you simply match local features, you will obtain a 3D model which is sparse. So you have only a few points for each surface. What people want from structure from motion, they want to have dense 3D model that they can use to fit surfaces or to have an understanding of the scene. So how can we do this? Well, just to recall something related to structure from motion. In the stereo, so we do a comparison with the stereo. In stereo, we have two cameras perfectly calibrated, okay? And this stereo, by using that coupling structure, coupling system that we have shown, allows you to have a dense reconstruction. We can say that for every pixel in an image, ideally, if we have enough texture, it is possible to find out a 3D point or a disparity, compute a disparity, and then associate the disparity to a 3D point. In structure from motion, instead, classical ones, we have one camera moving, there is no calibration, and this is a clear problem because we need to find out from the images with no other information which are the intrinsic parameters, the focal length, the characteristic of the cameras, and which are the position and the orientation of the camera. And also you have the problem of sparsity. So these are the main differences between the two strategies. In the structure from motion, we can have two different families of solutions. We have differential solutions where basically you analyze the speed of conjugate points, and we have discrete solution where you analyze the position of the points in the different views. And basically, this is a classical division of the structure of motion strategies. Anyway, recently, most of the approaches that we will see are based on discrete, especially if you're using heterogeneous collection of images. And the basic equations that is used in structure from motion is the Longue-Higgins equation that links the points on one image to the points on the other image. Or, more precisely, points belonging to the same 3D points in the image A with the points associated to the same 3D points in image B. Okay. Of course, this relation allows you to estimate, if you have this coupling of points, it is possible to estimate F, which is your fundamental matrix, which contains intrinsic parameters of the two cameras, the relative and position and orientation, and it's possible to process this image in order to estimate these quantities, and then get the image, the orientation and the position of the image. Of course, the simplest case is that when you have the fundamental matrix is known, okay, and in this case you can simplify this equation into this, where you can see here that E can be decomposed into a rotation matrix and a matrix which is associated to the external product, but is basically it is a matrix which can be computed from the position vector T. So the pipeline can be summarized in this way. You collect images in the wire. What you do? You compute the correspondences between a couple of images. And this is a crucial step in the structure from motion strategy because basically, for example, in Bundler, this takes about 60% of the processing time. And the problem is that it is an n-squared problem. If you have n images, you have to compare every couple of images with every image with every other image in the dataset. So it is n squared. If you consider that each image has m key points, okay, m descriptors, you need to match every descriptor in the image, so it's n squared, m squared problem. So this is why it is so complex, and a lot of people have tried to simplify things to find a faster way to solve the matching problem. Given the matching problem, so you have a set of points in image A, a set of points in image B, you can couple these points and you can compute the fundamental matrix using the Longue-Higgins equation. And so this is called epipolar geometry estimation problem. And actually, you can do this for every couple of images or do some easy stuff to do this. And then, after you have computed your matrix, you can decompose it into R and T by using different types of solution. We can say that different solutions have been proposed in these steps. This is quite standard because people know how to solve this in a mathematical way without any problem. And then you have the problem that despite you have done this, you need to refine things. And the refinement steps is a bundle adjustment strategy, which is a two steps iterative strategy. What you do, since you are estimating both the 3D points and the position of the camera and the parameters of the camera, what you do, you fix the parameter of the camera, and then you modify the 3D points in order to minimize a cost function. Then you fix the 3D points and you minimize or you change the parameter of the cameras in order to minimize the same cost function. And you do this iteratively in more than one steps, alternating one and the other minimization. So how do you basically match points? Well, we have different types of solutions. Initially, bundler, call map, all the other solutions used descriptors, local descriptors on images. The problem is that descriptors may be affected by a lot of things like noise, the fact that you have changes in the images, and especially if you are collecting the images in the wild, you have a lot of problem in descriptors, and you have the problem that they don't match one image on the other. So this is why researchers have proposed different way of matching elements in the different scenes. For example, so this is the classical method. You compute local descriptors on image 1, 2, and 3. You match these images, okay, you match these descriptors, and you have this matching which is local. Often these matches are wrong, okay, and so what you need to find a way to clean up the matching, removing the matching which are definitely wrong. This strategy is the same strategy, for example, that you use if you have to stitch images in Panorama, or if you have to do some object search, or that you use eventually for localization orientation in application like augmented reality. It's very close to. And you can use different types of local descriptor or key points detectors, and they have different characteristics. It depends, of course, on what is your complexity requirements and also which is your applications. For example, if you don't have constraints on complexity, you can use sift and surf, which are really powerful, really robust. You can see here for these query images, using surf, I'm able to localize the query images very accurately, okay? And you have many ones. The problem if there are other ones which are simpler to compute, smaller, like orb and others. And the problem in this case, those are used, for example, in robotics, in application that requires processing in real time. Of course, they are frailer, so you have to compensate the fact that the descriptors are frailer with some additional tools. It is possible to be more robust if you look for more complex things in images, like lines, for example. And in this case, lines are nice to look for because it is more robust. So if you have wrong matches, you can get rid of these wrong matches because we are looking for a set of points. And at the same time, if I'm looking for a line, I'm able also to find a dense set of points, because after I found, for example, the 3D points, the 3D coordinates of the two extreme points of a line, I can interpolate all the points in the middle. So it is nice to have the density, and it is possible to have something better if I use an object. If I use an entire object and I look for an object inside the image using, for example, an object detection strategy, in this case I can have a matching which is more robust, and at the same time I can be denser in my reconstruction. Other solutions are based on the neural networks. More precisely, there is an approach by Schoening and others from 2014. In this case, they target a single simple object, okay, and what they output is the reconstruction, but the limitation of this approach, or most of the approaches, there are other ones as well, but they take into consideration a single simple object. And then there is another approach of 2017. In this case, what they do, they use a CNN to estimate a depth between a couple of images, and then they use the transfer weights to basically integrate the other couples inside the reconstruction. Another solution is to use, instead of looking for points for object, is to estimate the transformation of one set of points and the others. And there is this network, which is really simple to implement. The name is homography net. This homography net is a network that, given a couple of images, want to find a couple of patches, okay, size 128 pixels, wants to find which is the transformation from one patch to another. And instead of computing the matrix H, which is basically the matrix that defines the mapping between the points of the image A and image B, they replace H with a matrix that they call H4. So instead of using H, which is a 3x3 matrix, they use H4, which is a matrix where is a 4x2 matrix, where you report the perturbation of the corners of the patch which has been perturbed. So what do? They say, take the image, take the patch like this, perturb the corners, and then generate after the homography from this perturbation. And this network here estimates the perturbation of the corners. The reason for doing this is that if you use the homography matrix, inside the homography matrix you have elements related to scaling, rotations, and other distortions. And especially for errors that you do on scalings, you have that the parameters of the matrix changes a lot. And so it is quite an unstable estimation. By estimating H4, it is possible for the CNN to have a better estimation. And these are the results that we obtain. Basically, we reproduce the same approach of homography net, but you can find a lot of implementation on the web, on PyTorch and TensorFlow. Basically, it is possible to see that if you have a strong distortion of the image, okay, you can see that the accuracy, this is the MSE computed in rectified images, it's much smaller for the CNN, training with LM, rather than with the classical approach with the SIFT. For images which are not distorted a lot, SIFT performs well. There is no difference between the three strategies. And actually, this has been extended to an unsupervised approach where basically they change, this is exactly the same approach here, they change this part just to make the system adapt to different scenes. Because the problem of this approach is that to be sure that you are able to estimate all the possible homographies, you have to train this on a lot of examples, generating a lot of random perturbation. Then, second problem in structure for motion is the relocalization. And relocalization means that given the image, given that I have already reconstructed a partial version of the 3D scene, okay, from coupling images, I needed to localize this image in time and understand where it has been taken. It can be done in a really classical way. Basically, this is PMP, solve PMP in OpenCV function, okay, where you have the 3D model, you have the 3D points and the 2D points, and given this, you can find the localization of the new image, or you can use some iterative strategy or some strategy using ransack to remove the noise. Some people, more recently, have proposed new solutions because the real problem is always the same, so matching key points. Still, I have to match key points, and this is a real bottleneck in terms of computational complexity. So the first problem from one solution is PoseNet, that creates a convolutional network that outputs the position of the points and the rotation of the position of the camera, and the position and the rotation of the camera, which is expressed using a quaternion. And then it is a regression network, okay, performance regression, and it's trained on a set of scenes. This has been improved by adding an STM layer at the end. So this CNN PoseNet is used to generate features, okay, and STN is used to find the correct orientation of the image in this second word here. And then we have a more recent work by Sarlin and others, where in this case you create global descriptors, local descriptors, and a map of key points by using HFNet. So in this way, this network produces these two types of descriptors, and hierarchical approach is used to basically understand how the camera is placed. So more precisely what they do, you take the global descriptors, you look inside the dataset for the images which is closer with respect to this global descriptor, and then you use the local ones, matching the local descriptors of the image you have found and the image which is the query, to localize the image. So you don't need to compare all the 60 key points with all the images in the database, and this speeds up the process. And then we have another solutions by the group. This is the group by Paul Face, okay, and basically they use, in this case, this has been applied to RGBD images, but actually we have RGBD images in the dataset, but the image I want to localize is a standard RGB image. So I use this 3D information to basically localize the data. So the problem of localization, the third problem that we have mentioned relating to FM is the next best view. So which is the order? The order matters, okay? So what does it mean the order matters? The way that they process images. So we said in structure from motion, we take a couple of images from my dataset, and I couple them, I create a partial reconstruction from these two images, then I add a third one, a fourth one, and so on. In a classic transform motion, this order comes naturally from video, because I will match frame number t for which frame number t plus 1. But in a heterogeneous collection, I do not know the order, okay, because the images are completely random. So the order can be anything. And the order matters. For example, let's consider two different datasets. These two reconstructions have been obtained from the same data. So I'm processing, in this case, I'm processing 40 images, the same amount of 40 images. So 40 here, 40 here. The only difference, the same algorithm, okay, the only difference is the order. So if I do a random inclusion of the images in the dataset, well, you can see in the reconstruction I have a lot of false, a lot of errors. If the order is the correct one, in this case we followed an order which was basically we associate one image with the image which is closer in space. We pretended to know in advance the localization, the place of the different images. So if you take the image which is correct in the order, you obtain from these 40 images a reconstruction which is much better. So knowing the order is fundamental, and that is why people have proposed different solutions. So in Snavely, this is bundler, you do an incremental using the number of matches, okay, from one image with the other. Then we have in Samantha, basically you have a hierarchical order. So you combine these two, you can then find that you have a lot of matches between these two, okay, and then you combine these two. And then at the following step, what you can do, you can take this 3D model, and merge them. Then we have another image with a lot of matches, then you can process this image as well. So it is a hierarchical ordering that allows you at the same time to have a better reconstruction and also to process image in parallel, because if you have multiple cores, multiple images, multiple machines, you can process these two and these two at the same time. And another solution is to use a global estimation, with the solution proposed by Jiang and others. And another problem that you have with the wilderness is the fact that images may have undergone a lot of processing steps. So we take this image here, this is the original image, and we can see here all the key points found through the SIFT detector. Then we apply some editing steps. In this case, the editing steps are compression. So we assume that this image has been taken, uploaded on Facebook or Picasa, and then another guy took that image and uploaded on another website. So after two editing steps, you can see that some of the key points have disappeared, and after 4 editing steps, okay, what you can see that you have that a lot of points have disappeared, so some key points are no more available. Not only you have that the key points that were matching, so the red one are the original one, and the yellow one is the one here, found here. You can see that these are matching in this image. In the 4 editing steps image, you can see that these are completely detached. And this creates a problem in the reconstruction, because this creates noise. If your 2D points has noise, it means that there is an uncertainty interval where the optical ray coming from the image goes into the 3D space, okay, master rate. And this creates basically an interval, 3D interval of uncertainty, which is going to be larger the more noise you add on the points. So the less precise you are going to be, both in the 3D reconstruction and also, of course, in the localization of the images. So how can you basically deal with this? Well, you can reduce this in using the correct ordering, and also avoiding to use images which are too crappy, they're not precise. Why using the correct ordering? Because if you include first the images which are more reliable, basically the reconstruction is a sort of descending process, descending optimization process. And there are a lot of local minima, but if you start from a good starting point, it is easier that you get to the global optimum. If you start very far from the global optimum, it is easy that your reconstruction ends in a local minima. So that is why, basically, the lowest amount of noise allows you to place close to the global optimum. And this is why you should use first the images which are better in the reconstruction. So how can you do this? Well, actually, what you can do, you can remove the links which are wrong. So if some matching are wrong, if some key points does not exist, you can remove this by using a round second. So you estimate an affine transformation one image onto the other. If a couple of points does not follow this affine transformation that you have estimated, you can get rid of. Of course, the model is going to be less dense. because you are removing some selected points. What you can do a pre-matching, remove outlier using another type of metric. You can use more complex parts, as mentioned before, lines, segments. You can use a semantic prior, okay, that if you know what you're looking for, what are the objects. And then you can use, for example, the projective SFM, which is a solution by Magellan and Dalbois. What we proposed, actually, this is the solution that we proposed, is based on a mathematical denoising of the matrix of correspondences. So what we mentioned at the beginning is that in the structure for motion you have this, and this basically, if I go back a bit, this is the matrix of correspondences, where for every image you have the number, okay, of key points matching this image with this image. And you can build a matrix with these correspondences, and this matrix basically tells you which image you should choose first. Of course, this image matrix is quite noisy because you have wrong matches because of the key points, because of the noise that you have added to the image. So starting from this noisy matrix, we can do something which is really simple, does not require a lot of computation, and it's quite fast. Basically, we can model this matrix as an Euclidean distance matrix. More precisely, given that you have, this is the 3D object, these are the cameras, it is possible to basically associate to every camera a vector, a binary vector, which has a length which is equal to the number of points I want to reconstruct, the number of points on the scene. And for every position of this vector, I can place each element to 1 or 0, depending on whether this image sees the point or not. For example, this is image number 0, okay? This image sees 2 points of the scene, P0 and P1, which are placed in M00 and M01. Very well, in this vector, I will place these points as 1, 1, 0, 0, 0, okay, because the first 2 are seen. Similarly, this is 1, 1, 1 because I see only the first 3 points. This is 1, 1, 0, 1, 1 because I do not see the third point, okay? So given this vector, I can, with a few counts, I can show that basically, if I compute the distance between these couple of vectors, I can generate a matrix, which is an Euclidean distance matrix, because I'm using a Euclidean norm, the Euclidean distance matrix, which is basically connected to the matrix of connections that I showed you before. So the matrix of correspondences is basically can be mapped into this. And why do you may ask, why do you like this to have this Euclidean matrix? Because Euclidean matrices have a lot of mathematical properties, and the most important one for our work is that if you take this geometric centering matrix, you take the distance matrix, and you multiply this matrix by this, as this, basically the resulting matrix must be positive semi-definite. But if you have noise, it is not going to be positive semi-definite. For example, here we had a simulation, and we added the noise on our key points. We computed the distance matrices, the correspondences matrices. We computed the associated distance matrices. And you can see that if you increase the amount of noise on the points, you can see that the number of eigenvalues of the matrix, which are greater than 0, greater or equal than 0, reduces. And you know that in a positive semi-definite matrix, you must have all the eigenvalues 0 or greater than 0. So, what can we do? We can impose in this matrix, by using an iterative procedure, that the matrix must be semi-positive, semi-definite. And by doing this, we obtain the correspondence in matrix that is denoised and that we can use in the ordering process. More precisely, to give you, skip all the mathematical details, I can give you if you are interested, but intuitively we can say that given these 3 images, which images should we use first? Well, actually, given this, I have that we have more links between this and this, so I should use this link and this link, okay? I should not use this link, despite, if you look at the images, okay, this is very similar to this, much more than this and this. This is because of the noise. So, what is the function, how this algorithm works? Basically, what this algorithm do, they exploit the bigger guys in the matrix. Those guys that has the more link with the others. And what this bigger guy says is that, okay, don't trust this guy. I have a few links with this, there is a lot of noise, this is completely crap. So you should link with these 2, don't use this image, despite the local information tells you that the matching between this and this is better than this and this. Okay, so this is intuitively what this algorithm do from a mathematical point of view. And then these are some results regarding this. I think that I'm going to finish. So you can see that if we look at the variance of the 3D reconstruction model using this ordering, it's possible to have a much better results. And here you can see that in this heat map, the color is associated to the error. Okay, and you can see that if we compare, for example, the heat map with the proposed solution and the original bundler, it is possible to see that the errors that we have on our reconstructed model is much lower with respect to the error that you have in the original algorithm. Same algorithm, same amount of images, okay? What is the difference? Is only order, okay? And these are other examples regarding this. You can see a lot of artifacts which are removed. And this is the case of Notre Dame Cathedral. We can see that here the reconstructed doors is much better than this. Here there is a missing part here. And another solution that you can do basically is to work on the cost function of the bundle adjustment. In this case, basically what we have seen, for example, in the multi-camera scenario, it is possible that you have many cameras watching the same scene. But what is interesting is that what happens if I know that my camera here see this camera here? If I know that this point, the blue point here, is the projection of the point on the image plane of this camera here. This happens especially if you have a system which is coordinated, like a system of cameras, a system of drones, for example, which are flying in patrol, okay, over the city. And it may happen that you have multiple drones, that one drone is looking at the others. We call this condition camera in view. The camera is in the view. Why is this nice? Well, according to the traditional structure for motion, okay, or traditional reconstruction problem, this is a 3D point, because it is a pixel that belongs to reality, it is an object. But this 3D point is at the same time one of the camera parameters, because it is the position of the camera forward. And if I know this, if I'm able to detect this, I can use this in my minimization function, creating a much more robust solution. So in the bundle adjustment, usually what you do, you minimize this. Points, parameter of the cameras, and 3D points. So what you do, you know this, you fix this, and then you minimize this, then you fix this, and you minimize the parameters. If you know this, what you can do, you can add an extra constraint, basically, that regularizes the minimization process, and you obtain a much better solution. For example, we apply this. This better solution can be applied by adding this, or what you can do, you can also check how good is the link. For example, if these two images are badly coupled by this metric, I can remove this link. I can avoid using this link, saving time and saving also, improving also the precision. So this is an example that we have done in this concept. Actually, we have it's a really toy situation. We have multiple cameras. One camera is the one of the cell phone that is mounted on a Lego Mindstorm robot. And then you have one camera is the one recording the scene, and there is another camera, a third camera, which is recording the two cameras. So we have possibly two cameras in use in this condition. So if we look at the reconstruction that we have in this simulation, it's possible to see that using this information, the reconstruction converges much earlier, okay, and it's much more precise. And if I can show you some details, some numeric details, we apply this to a pattern of drones. In this case, we wanted to have 1,000 drones. We didn't have the money to buy 1,000 drones. So that's why we simulated using computer graphics. And using computer graphics, we can simulate this camera going around the city. And it's possible to see that in this scenario, we have an improvement in quality. And at the same time, we also have a convergence which is much faster. You can see that camera in view allows you to converge in terms of accuracy with a lower amount of frame, with a lower amount of seconds. So it is possible, in the end, I conclude, to include also the information regarding the processing history, so the focus of the image. Since you have to estimate as well the intrinsic parameters, what we did in this approach is to use some forensic metrics to understand which image has been taken by a camera which is similar to the camera of another image. And then what we do, we cluster images first, we do a partial reconstruction between images and cameras which are similar, and then we merge the reconstruction, okay, into the general one. And also using this solution, basically it is possible to see that the quality of the estimation of the 3D points and also of the intrinsic improves a lot. We added as well a processing age matrix, so we wanted to get rid or use first the images which have been processed with a lower amount of processing steps rather than images which are have been posted and uploaded a lot of times. And this is why we introduced this metric which is called processing age, because it's the age in terms of processing steps which can be associated to an image. It is a no reference quality metric that can be included in the reconstruction, and it's possible to see that you have a much better reconstruction than the standard algorithm. And then actually conclude basically all this strategy, okay, they are focused on choosing, identifying the reliable data. So the first, if you want to have an accurate reconstruction, the data must be reliable and use all the quality elements, all the tools that you have in order to identify those reliable things. And then include, you can also use the less reliable one, but you must include the later step, so after the first, the high quality ones. What you have to also to use extra constraint if you have it. And then basically you can also rely on, if you know something relating on how the images were taken, use this additional information. So if you have some forensic stuff that tells you that this image has been taken by this camera in this condition and so on, use this information because it can improve a lot, both the density and the quality of the 3D model. Of course, in the future direction, here we are focusing on merging different types of data, okay? And of course, it's possible to use text, videos, images from different cameras, prior information about the scene, merged it. And also, what people is focusing now is also focusing on sensors which are different. There are a lot of works using RGBD cameras, so you have that information as well. At the moment, in Padova, we are also focusing using RF cameras. So we have cameras which takes a 3D scene using, it's a radar, okay? And is it possible to include this RF information inside the construction as well? I thank you very much. Sorry for being a bit longer than expected, but.
Yes, there are no questions.
Yeah, we have questions.
You have questions.
They just need a jumpstart.
Yeah, I know. There has to be somebody.
Lavi has a question.
Lavi, please.
Thank you so much, Professor Simone. Nice talking point for us. I have a couple of questions. I was wondering how those 3D reconstruction methods, as you mentioned, can be worked out on the unclean data, which are basically collected from the social media, and it contains mostly junk data and a lot of duplications. So I was wondering how can be a possible behavior of those methods and this kind of. Let's assume, for example, 30% of the data are the positive, which are our interest, while 70 are the jumps and duplications.
Okay, so we're talking visually. Junk data can be for different reasons. So we can say distinguish two different classes. Junk data, which are junk data, they are not related to your problem. For example, let's say Notre Dame fire. To mention an example that you know, I can put an image and write the tag Notre Dame fire, only to have it visualized a lot of times to acquire. So in that case, when you put the image inside the dataset, you won't find matches, it's going to be thrown away. For sure, if you know this in your dataset has nothing to do, basically it is better for you because you save a lot of computational time. So what you can do, you can use global descriptors for the image first, and then after you have removed the global descriptor, you can enter that. Then there are data which are not reliable because they have a lot of noise, or there are a lot of missing details, okay? Or there are some details which are reliable, okay? But there are only a few ones. That is the point. If you're using the number of matches, it may happen that you have strong key points that you can use that image, okay? But the number of key points that you have found and you have matched is low. In that case, you should use some coupling metrics, so you can see that if you match these key points, okay, with the other images, there is a transformation which maps these key points very well. So in that case, despite you have junk data, you have only a few key points, you still can use the image. So the idea is to use metrics, as many metrics as you like, to understand this situation.
The second question was like, how the quality of the image, like referring back to those collected images from the social media, which are basically has low quality of the images. So what is the possible trade-off can be gained in terms of the quality of the image and the performance of those reconstruction methods? Okay.
It depends of what you want to reconstruct. Okay, in the sense that even if you have the best idea is to associate the quality of the image to the type of descriptors. So if you have a descriptor which is really strong, okay, you don't care about the quality of the image, and you can use only for that descriptor that image, only for that 3D point. If you have a 3D point which has, is a bit frailer, let's say high density texture, if you do a lot of processing, an image which has been posted many times on Flickr, that texture is going to be ruined a lot. In that case, you should avoid using that image. You can do this by checking the characteristic locally of the image and checking, for example, what the descriptor do there. I don't know if I answered your question.
There is another topic to be seen, that is the hindering of a scene by a new viewpoint. How do you think that this set of methods can be used for reconstruction a scene by elucidating data for viewpoints that you don't have?
Okay. Yeah, actually, in a calibrated setup, this is a really well investigated problem. It's the problem of virtual views. So you have multi-cameras, and you have, let's say, 30 cameras around the scene, 3D scene, and you want to have something in the middle that you don't have in reality. Okay. In this setup, basically there are a lot of methods based on accelerator that do this also in real time, especially for, let's say, entertainment industry, sport events, and so on. The problem in this case is that you don't have a calibration. So it is still possible somehow in this scenario if you have enough images. So I think that the problem of generating virtual views is to have a lot of images that to process in all the directions. Because one thing that you usually have when you crowdsource the data is that you don't have the same distribution from all the viewpoints. For example, for Notre Dame, the dataset Notre Dame that you download, not the one from the dataset that you download from the site of Snabely or other ones, you have a lot of images, but most of them are taken from the facade. Okay, because most of the people take an image from the facade. So the real problem, okay, in structure from motion is that most of the images are not evenly distributed. And if you have that from one specific viewpoint, your image is not reliable, there is no solution. So you don't need a lot of images, 1,000 of images, but you need the good ones. Okay. If you have lots of them, you can infer a good one, or you can find a good one. But if you have a few, and unfortunately the few ones that you have are not high, with a high quality, you're done.
I have one here. In which industries have we been using this? You mentioned that, for example, forensics. I don't know if we're actually using this forensics nowadays. For example, I can mention in the industry, entertainment, for example, I haven't seen this in movies before, I have seen this perhaps in sports advertisement, but where is the industry today actually being using this? Because I think it can be used in the future, but can you already use this for forensics, for example?
Okay. Actually, in our works, we used forensic to do reconstruction. So it was an inventory process. So we use forensic to do 3D reconstruction.
Right.
If you want to have a very nice overview, you can talk to that guy there, which is an expert on this, because he's still working on this. So use this type of strategies on forensics. What I know for sure that there are some approaches in, let's say, forensic and legal stuff to use these graphical tools to do reconstruction of scenes, crime scenes, and so on. So there are some approaches that have been tested using 3D reconstruction, for example, combined with some enhanced visualization things, maybe. So some virtual reality solutions to use this to reconstruct the scene. So what do? They use photometry to reconstruct the scene. When people go to the crime scene, there are policemen taking pictures. Okay, in that case, they reconstructed the scene using these types of solutions. So, in a forensically speaking way. Okay.
Right. Would you mention another industry in this that uses this?
Okay. Many ones. Actually, entertainment. I've a project with archaeologists. They use archaeologists in this to reconstruct a website. For example, they use the drone flying over an area, an excavation site, and then they do the full reconstruction of the excavation site. We built a museum in Italy using these types of solution, using this. They are used many other archaeologists. It is used especially for architecture as well.
Can I give one example? Can I complement one example and then send an advertisement as well?
Yeah.
Thank you for your question. For those of you who are interested in seeing this in practice, in October this year in São Paulo, for the first time in the museum of, it's called MIS, I think it's Image and Sound. There will be the first exposition using more than 300 projectors and 3D reconstruction for all of the works of Leonardo da Vinci. So if you want to see how this applies in using computer vision, computer graphics in real life for arts, it's very interesting that you put in your agendas MIS, Museum of Image and Sound in São Paulo in October. So 3,000 square meters of Leonardo da Vinci with more than 300 projectors. So I needed to do this advertisement. The question was nice.
Actually, I can advertise the museum, the big creative, but it's a bit fun.
And I'm not like part of the museum, okay? Just because I love art.
Or another one is remote relevance. For example, from satellite images, they use structure from motion to match images and have a 3D reconstruction of the Earth. Also, including different types of sensing, so different frequency, different type of images. So it is widely used in many uses.
Thank you.
There are some other examples. For the mining industry, you had the open party and you use drones, and you had a photo surface, you use computational photogrammetry, and you had this 3D view reconstruction. Also, from you had a kind of disaster, also used to make a plan for future mitigation.
Actually,
So you can make a lot of money out of it. If this was the question, the answer is yes.
Also, because in these specific problems, you have some issues that need to be dealt in that specific. So it is true that it's a structure for motion, okay, it's a for motion, but there are some issues which are specifically for this application or the museum, which needs to be dealt very quickly, very accurately. For example, we don't have atmospheric problems And if you fly a drone at very high altitude, you need to deal with that. And this creates that your point is not really stable in the image, and you need to compensate somehow. Yeah. I see. Okay.
So I have one as well, but go ahead.
Yeah. When you're using global descriptors to then create local descriptors, then how do you first acquire the global descriptors? Is it by images, by the original images?
Yeah. Actually, you don't create the global from the local. Okay, you have a global and local. Then depends. Okay, there are different algorithms to do this. But the idea is to have an image with a single descriptor, and so you avoid comparing all the local descriptor with all the local descriptor of the others. But first, you have a single image. You have a sort of signature of that image, and you look for the image in the dataset which has the closest signature. This is one possible solution. But this is not the only one. Other people do this. They take the global descriptor, they convert it into the simpler global descriptor, like binary ones, okay? And then they do the first matching on the binary ones, and then they refine on the real local ones. It's a sort of, global descriptor is a sort of, let's see this as a simplification, okay? To save time in the comparisons.
You are the guests. I'm here just to allow you to do a lot of questions.
Is there any ongoing research on classification or segmentation on the cloud, on point cloud, from 3D reconstruction in your department?
Yeah, this is the other thing that we do, okay, on point clouds. More precisely, we are more concerned about the coding of point clouds. Since October 2017, there is an initiative by MPEG in order to create a new point cloud standard for point cloud compression. Okay. The nice things about the standard is that it should target any type of point cloud. So basically, you have point cloud from structure from motion, which can be really sparse, and you have point cloud from 3D models, okay, from depth camera, okay, from LiDAR. This standard is supposed to take care of all possible things. And at the moment, we proposed some solution for point cloud compression, and now we are focusing on segmentation. The idea is that you wanted to distinguish different parts of the point cloud, and you do the segmentation. Other guys, I know that there are some segmentation strategy for point clouds applied to structure from motion, used to fit the surface. In order to have, for example, a dense, okay, model, it is nice if I know that I have 1 point here, 1 point here, and 1 point here. It is nice if I'm able to detect that this is the table I can fit a plane. And this is nice because I have a dense model. So there are some solutions that works in this way in order to segment correctly point cloud, identify planes in different part of the objects. And then if you go in the robotic world, actually, which we know, we're more signal processing guys. The robotic world, there are lots of works related to the segmentation of point clouds, because in a robotic problem, if you're able to segment an object, you know where the robot needs to grasp the object instead of this. I checked the solution. I can provide you some references if you are interested in that.
I'm just starting right now a research about it.
Yeah, but there are, you can check the challenges that they've been published, that the robot has to. There are several ones. I don't want to say something wrong, but actually I have the references in my PC. I can give you some references to start with.
No more? Yeah?
Good afternoon. Just curiosity, quite simple. University of Padova. You exposed here those methods for 3D reconstruction. University of Padova have been developing solutions, applications, for example, for smart cities or healthcare, dedicated for this.
Okay. So all the solutions that you saw at the end of the talk, starting from the forensic stuff, is a solution proposed by University of Padova, the ordering. So all those are methods proposed by University of Padova. We're still working on the project. The work in the last years that we have done, we use this solution to do compression. So basically, I use structure from motion, reconstruct, and use this for compression. in the recent years, we focused on including forensics into structure from motion. But actually, in the future, we're going to see what's happening. At the moment, we are also focusing more on having a reconstruction which is more reliable, reducing the noise. That's the point. And the reason is that if you use this, for example, the new visor, like for augmented reality visor, to show these models, if you have 10,000 points, if you have 10 billion points, it makes a lot of difference. And if the billion of points is just noise, I'm wasting the resources of my device without any improvement in the quality of the visualized model. So this is what we are focusing on in this part. But we have done different things, starting from compression to reconstruction to the ordering to including this type of metrics into the 3D reconstruction process. Also, neural networks, okay, we have investigated, but yeah, there are a lot of guys which are working on that, so we prefer to go to paths which are still unexplored. Okay.
I saw that you are using superpixels for a processing step of segmentation. For that, you are using just the distance and the color space to the...
You mentioned the first slide.
Yeah.
Yeah, the first slide is a method by Make 3D by Saxena. They're using superpixels on simple color. Okay. Yeah. What we are doing for semantic segmentation, we are using we are doing that on superpixel, and we are growing. It's an bottom up and top down approach. Okay, and we are using. We have done that for standard images using RGB plus class. Okay, of the pixel, so which is the classification that you get to the pixel. We did this for RGBD, where you have RGB, depth, and class of the pixels. So we're using this 4 or 5 information on that.
So just to conclude, thank you very much for your talk. Going back to the questions of Lavi and our colleague here. So you mentioned that one way of getting rid of the junk is processing the image first with a global descriptor. For instance, you can get the image, you can give it to a neural network or convolutional neural network, get the feature vector, and use some metric to filter the ones that are closer. But imagine that you have a dynamic event and you want to recreate what happened for that dynamic event. For instance, instead of just recreating the 3D view of Notre Dame Cathedral, what you want is to recreate the moment of the fire of Notre Dame Cathedral. Exactly what we are doing for the Deja Vu project. So the forensic here, what we do is we collect things from social media and we want to recreate events and then to tell the story about what happened. So the beginning, the duration, and afterwards. So in that case, I think that there is a serious problem, right? Because if you use a global descriptor, you are not going to capture the property of the dynamics of the event, because the global descriptor will focus on the fixed, the static parts, and we will get rid of the fire parts, and then everything that's going to be selected will be the cathedral, but not the fire. So this is the open problem that we are investigating now, and global descriptors for us is not working.
The difficulty is to do this for images. Because, for example, for videos, you can use the time, you can use something which is dynamic, and you can down, for example, there are a lot of applications in computer. Disney has worked many years with this to do detection for motion. But for images, it's a really quite hard problem to know from a single image to locate this in time.
And then you have the second problem, which is you need to discard images from previous times, because we want to focus on reconstructing that event in that time. So it doesn't matter if I receive an image from the Notre Dame Cathedral from 1 year before, because I want to focus at this particular time. And as you have seen from our first results, I don't want to see images from the movie of the Hitchcock of Notre Dame, because there is a fire in that, and the algorithm is detecting fire in the Notre Dame Cathedral, but not that kind of that
people
fire image.
Not people seeing it, right?
So Disney has done all our work and done it.
Yeah. All right, so
Don't you have a bunch of videos of the fire that can help you?
we have.
You mentioned that the videos are.
Well,
easier to
this was one of our surprises. So we collected the data about the event, and we collected more than 25,000 items. But the thing is, most of them are junk. So it seems that people love to get like one good view of the event and replicate.
Right.
So there are a lot of duplicates, and they just want to grab views in social media. And at the end, if I'm not mistaken, Lavi can correct me, I think that we have 2,000 things that are usable out of the 25,000. Yeah, 2,000, right? So it seems that this is common for many events. People just like grab what they have and republish, repost. So we have some videos. Videos might help, but what we want to do is to put together videos and images and photos.
Because I guess what happens is also when somebody finds a beautiful view, and not pardon for the word, but a beautiful view of a big fire, that they don't want to take a picture here or the back of the cathedral.
Exactly.
They want the huge fire that will make impact, right? And all, I guess
Yeah,
like
they
80%
want
of the pictures are the same
They
fire.
want an impact. Well, two things that they want normally. They want to have an impactful photo, and they want to show that they are there. All right.
Okay.
Any other question? No?
Thank you again.
Thank you very much.
So you send the transparencies to Anderson. You may send both of the University of Padova too. So I put them together.
A larger one, hopefully. But
Yes, it's the larger one, so we publish both.
Because there are other utilities almost
Go ahead. Yes.
So at 4, I'll be back for the meeting if you want to join us.
Okay, so yeah, I'll go.
Okay.
And yes, I will prepare a version.
Sure. Just send it to Anderson. Forward it to me. Okay. Thank you very much. Very nice meeting you. Now, as always, yes. São seminários normais, mas não fazem parte da produção. Hoje não, nem dia só no dia 16.
Seria mais barato se
Yeah, they're trying to create a system to segment and classify trade lines. And they're trying to use PointNet, which is a